Welcome to Curium. As part of Tool 1, you are expected to be able to measure the mass and volume of a gas and then use that data to calculate its molar mass. Note that this concept could come up in paper 1A or paper 2, but the experimental aspect is particularly likely to come up in paper 1B. There are some key concepts that will be helpful for you to understand before we begin. First, what is Avogadro's law? Also, the PV equals nRT equation or the ideal gas equation. Note that this equation is given to you in the data booklet. Let's begin by discussing Avogadro's law. This law states that it doesn't matter what the gas is, if you have the same volume, it will contain an equal number of particles, provided it's at the same temperature and pressure. So, as you can see in the image, I have 3 different gases present, and each of them will have a different mass, because each gas has a different molar mass, but because they have the same volume, all of them contain an equal number of particles. It's important to stipulate that they're at the same temperature, because if temperature changes, then the volume of the gas changes. These figures are stated for you in the data booklet, so you don't need to record them. And if they tell you in a question that the temperature is changing, they will give you the new volume of that gas. The idea is, if it's at STP, a gas will occupy 22.7 decimeters cubed, whereas if the room is a little bit warmer, then it will take up a little bit more space and will expand to 24 decimeters cubed. Both of these is the volume that 1 mole of a gas would occupy. For the ideal gas equation, units are particularly important. So your units for pressure should be in pascals. For volume, it should be meters cubed. Your units for moles will always be MOL. The value for R, the universal gas constant, is quoted for you in the data booklet, and your temperature must be in Kelvin. So if you're given kilopascals, then it's important that you multiply the value you're given by 10 to the power of 3. You may be given decimeters cubed or centimeters cubed for your volume, and you just must divide them accordingly. The value for R, as mentioned previously, is in the data booklet. And for temperature, the temperature will likely be given in Celsius, so you want to convert that to Kelvin by adding 273.15. Note that you may need to calculate the number of moles present using the formula N is equal to M divided by MR. Or at the end, you may end up with a volume and you use that to calculate the molar mass of a gas that's present, because you would link it to the mass of gas that you input initially. Now let's discuss how we can collect the data which we will use to calculate the molar mass. The data that we need to collect is something that we could input to PV equals nRT. Hence, we're going to need to collect the volume. The problem with collecting the volume of a gas is that if we try to use any of the regular pieces of equipment that we use to measure volume, like a graduated cylinder or a burette, the problem is that that's already filled with air. So I can't be sure that the volume that's occupied is only the gas that I'm actually trying to measure. Hence, what I want to try and do is fill that piece of measuring equipment, the volumetric equipment, with something else. And what I do is fill it with water. So I fill it completely to the top with water and then turn it upside down in a basin of water. That way I can be sure that the only thing inside in the graduated cylinder is water and not any other gas. Then I'm going to try to input the gas. But before I do that, I'm going to measure the mass. So probably the container of gas is either going to be a lighter, as was an example in a past paper question, or else maybe a canister of gas. If it's a lighter, you can simply just hold it under the graduated cylinder. But if it's something like a canister of gas, then you would probably need to connect it via a tube of some kind so that the end of the tube comes up under the graduated cylinder. First, I'll measure the mass of whatever that canister of gas is, and I can use either a regular top-loading balance or else an analytical balance, depending on what's available. The benefit of the analytical balance is that it has more decimal places, which means that your uncertainty would be lower, so that needs to be considered. Now that I have the mass of the container which holds the gas, I'm going to release some of the gas into the graduated cylinder. This is going to displace the water. Once I'm done, I just get the new mass of whatever the piece of equipment is. So what I've essentially collected here is a volume of gas, which will be the volume of water which was displaced, and I'll have the mass of the piece of equipment before and after the gas was released. In this video, you can see an example of gas being released and water being displaced. Now let's process some data together. You have recorded an initial and final mass of the container that held the gas, the volume of water that was displaced, and the temperature. First, we find the difference in mass, as this value will indicate the mass of gas that was released into the graduated cylinder. Next, we need to make sure that the units that I'm inputting into PV equals nRT are correct. So I convert my temperature to Kelvin, my volume to meters cubed, and my pressure in kilopascals into pascals. Note that the value for pressure is given to you in the data booklet, and this is an assumption. We can assume that the pressure at STP or at sea level is the same as the pressure that's in whatever the environment that the experiment is being carried out in. Of course, it's better to measure temperature if you can, but you could also assume that it was the same as standard ambient temperature pressure. From the data booklet, I also get the universal gas constant value, and then I just can input these into PV equals nRT, again, given for you in the data booklet, and I just rearrange it so that I'm figuring out the number of moles of the gas that was added. When I do that, my number of moles works out at being 2.42 by 10 to the power of minus 3 moles. And now that I know the number of moles and I know the mass of the gas that was added, I can use that to identify the molar mass of the gas that's present. This next question would be considered an easy paper 1B question and is worth 4 marks. So there's an option to pause this video, set a timer for 6 minutes, and rejoin us as we discuss it. The question is essentially asking you to list the variables that you would have to measure in order to determine the molar mass of the gas. So think back to the experiment we just did. The first mark is given for you identifying the fact that you would have to collect the pressure, the volume, and the temperature of the gas. Now we want to think about how we could process that data. So we would process it using PV equals nRT, but of course I'd need to calculate the number of moles using N is equal to M over MR. That's worth 2 marks. And your last mark is for identifying the fact that you would also input R, which is the universal gas constant, which you would take from the data booklet. This next question would be considered medium difficulty, and as it's also worth 4 marks, there's an option to pause the video, set a timer for 6 minutes, and rejoin us as we discuss it. The question tells you that the molar mass of a volatile organic liquid, X, was vaporized at a particular temperature and pressure, and a certain mass of it was input into a gas syringe. So it's a slight manipulation of the setup that we have discussed already, but the principle behind it is the same. The temperature is at 90 degrees, and the pressure was recorded at 1.01 by 10 to the power of 5 pascals. You were also told that the volume of the gas recorded was 95.0 centimeters cubed. As with all questions involving PV and RT, it's going to be key to convert your units. So you need to make sure that your temperature is in Kelvin, that your volume is in meters cubed, and that your pressure is in pascals, which was conveniently given to you that way anyway. Those unit conversions, that gets you the first mark. Then you need to input those values into the PV equals nRT equation and calculate the number of moles. This will get you marks 2 and 3. You were also given the mass of gas that was input. So now that I know the number of moles and I know the mass, I can use it to determine the molar mass.